Welcome to this lecture. In the last lecture, we are looking at how resources can be shared among tasks in the framework of task scheduling, maybe a rate monotonic scheduler or an earliest deadline first scheduler. And we had discussed about critical sections, semaphores, which are basically topics that are discussed in the first level operating system course, and we did not really spend time discussing semaphores and critical sections, but then we had remarked that the semaphore solution used in a traditional operating system cannot be used as it is in a real time application, because it can lead to severe problems, and the problems are known as priority inversion and unbounded priority inversion. A simple priority inversion arises when a low priority task has locked a non preemptible resource and a higher priority task cannot execute and just waits for a resource. So, we have a priority inversion example where a low priority task is executing and high priority task is waiting. But then the priority inversion problem by itself is not too bad, it can be solved using careful programming, as you will see. But then what really is a difficult problem is unbounded priority inversion, where the low priority task which is holding the resource is preempted from CPU uses by other intermediate priority tasks which do not need the resource. Towards the end of the last lecture, we were discussing about a critical section and how priority inversion can arise, unbounded priority inversions, and what are the solutions. Now, let us look at that same example, that we have task T1 and task T3 that need to share a non preemptible resource. That means, they need to access that resource in exclusive mode, and only when a task which is already using the resource completes its execution using the resource, the other task can use it. Both the tasks have the following type of code. They have some part of the program where they do some processing without using the resource, but then when they want to use the resource, because it is a non preemptible resource, before they start to use the resource, they invoke Px, which is basically wait for semaphore, and after getting access to the semaphore, they start executing the shared resource. And after completing the code segment here, after the part of the code using the shared resource is over, they execute the instruction Vx, which is signal semaphore to release the resource, and then more local processing without using the resource. The part of the code in which the shared resource is used by a task starting with the same wait signal till the same signal is the critical section of the code. Now, let us see how the priority inversion in such a situation can arise. We have a task T3 which is of low priority, does some local processing denoted by L, and then after some time it gets into the critical section. So, before starting using the resource, it does a wait semaphore, and because the semaphore is available, it could get the resource and starts executing using the resource. but at that point of time, that is t, a high priority task which is T1 starts executing, and it does some local processing here, and until a point t plus 3, where it gets into its critical section and does a lock resource or a sem wait instruction execution. And since the resource is already held by T 3, the task T 1 gets blocked, and once it gets blocked, T 3 becomes active, uses the resource, and after some time at T plus 4 it completes the execution, and then T 1 gets the resource, starts executing, does local processing, and then after it completes, then T 3 gets the CPU and starts executing. So, this is an example of a single priority inversion, and the time for which the task T 1 gets blocked is between T 3 and T 4, where the task T 3 completes uses of its critical resource. Then let me just ask this question, that what is the maximum duration for which task T 1 can suffer priority inversion? The answer to this question is that it is equal to the largest duration for which the task T 3 would need to use the critical resource R. Now, let us look at the unbounded priority inversion problem. Due to the same resource R, the task T 1 can suffer two priority inversion when the task T 2, which does not need the resource, starts executing and preempts T 3 from using the CPU, and therefore, T 1 suffers two priority inversion, one on account of T 3 and the other on account of T 2, because T 2 is executing and T 1 would be waiting because it does not have the resource, and T 3 is holding the resource and not being able to execute because T 2 has started executing. So, there are two priority inversion, as you can see. One is on account of T 3 for this duration, and another on account of T 2 for this duration. If we extend this example, we come to the example of a unbounded priority inversion. Here we are considering multiple intermediate tasks here, intermediate priority task. T 3 is the lowest priority, T 1 is the highest priority, but there are T 2 1, T 2 2, T 2 n, etc. These are intermediate priority tasks, and once T 1 blocks for the resource for T 3, the intermediate priority tasks keep on executing one after the other, and T 1 keeps on waiting for T 3 to be able to get the CPU, complete its execution, but by that time T 1 misses its deadline. So, there is application failure. Unless the unbounded priority problem is handled adequately, a real time application can fail. There are many examples in the past where application failure was caused by this problem of unbounded priority inversion, but possibly the most celebrated example is the Mars Pathfinder. Let us see what happened there. Mars Pathfinder landed on the Mars surface on 4th July 1997, and as it entered the Mars surface, the vehicle which is the Sojourner rover. It was surrounded by airbags. Slowly it dropped down onto the Mars surface. It moved out from the airbag onto the Mars surface and started transmitting to the Earth station large amount of data. And these data included pictures of the Mars surface, and which were released by NASA and were publicly available on the web. A few of the pictures here, a large number of pictures were transmitted by the rover. One picture of the Mars surface, the rover has landed on the moon surface surrounded by bags and started taking pictures. This is another image from the Mars Pathfinder courtesy NASA, released to the public. But then the Pathfinder began experiencing system resets. The system, after every few seconds, started resetting itself, and as a result data could not be transmitted. Only a part of the data would be transmitted, and it resets, and again it starts transmitting and resets. So, complete data could not be transmitted. Newspapers at that time, they reported that the Mars Pathfinder is experiencing failures, and the terminology they use to describe the failure is there are software glitches which is causing the Pathfinder to fail. Some other newspapers reported that the computer in the Pathfinder was trying to do too many things at once and therefore was failing, and so on. But then in the laboratory in NASA, they were desperately trying to fix the bug. In the Mars Pathfinder, VxWorks, which is a real time operating system from the Wind River systems, was being used, and the rate monotonic scheduling of threads was used. And in the Pathfinder, different tasks, they shared they shared information through shared memory. One task would write to the memory and other task would read it, and so on. So, the different components of the spacecraft could communicate with each other through shared memory. To debug the Pathfinder, the NASA scientists, they had a replica of the Pathfinder in their lab. They started doing a simulation of what used to happen on the Mars surface, but they set the debug mode on, where they can find out when context switches occur, synchronization among objects take place, when interrupts occur, all these they could see. And finally, after several hours of working with the replica of the Pathfinder, they could converge on the precise conditions under which the reset occurred. They found that there was a mutex, a semaphore that was being used, and a Boolean parameter, a global variable was used, which was a Boolean global variable, and depending on whether it is the value of the Boolean variable, whether the priority inheritance is to be performed or not, that was indicated by the Boolean parameter. We will see what is meant by priority inheritance, but then they found that the Boolean variable had set the priority inheritance off, and they could on their replica of the Mars Pathfinder found that the problem can be solved if the priority inheritance could be turned on. And then they uploaded a short C program onto the Mars Pathfinder, and then the unbounded priority inversion that was occurring could be tackled. In summary, I can say that the Mars Pathfinder was experiencing problem because the solution to the unbounded priority inversion in the form of a priority inheritance procedure was disabled by the Boolean variable. So, they enabled the priority inheritance procedure, and then it could solve the unbounded priority inversion problem. Now, let us see what are the solutions for the priority inversion and multiple priority inversions. First, let me ask this question that if a task is a high priority task is undergoing priority inversion on account of a lower priority task, what is the longest duration for which the priority inversion can occur? If you think of it, we had actually mentioned it only few minutes back. We had said that a single priority inversion can occur for a duration that is bounded by the duration for which a lower priority task needs the resource in exclusive mode, or in other words, the maximum time for which a high priority task can suffer priority inversion on account of a lower priority task is the maximum time for which the lower priority task needs to execute its critical section. Given that the time for which a lower priority task needs to use the critical section is the time for which a higher priority task suffers priority inversion, can we solve the single priority inversion problem through careful programming? The answer is yes. We can solve the simple priority inversion problem through careful programming. We can restrict the time for which a low priority task uses its critical section. Each time there is a consistent point in its uses of critical section, it just releases the resource. So, through careful programming, the duration for which a low priority task needs to use the non preemptible resource can be made very small. A simple priority inversion can be taken care by careful programming, but we will see that the unbounded priority inversion problem cannot be handled in similar way through careful programming. Let us see how to solve the unbounded priority inversion, because this is the difficult problem. Simple priority inversion can be solved through careful programming. The solutions to the unbounded priority inversion are called as protocols for resource sharing among tasks. The simplest of these protocols is called as the basic priority inheritance protocol. It was proposed by Shah and Rajkumar 1990. The main idea behind the basic priority inheritance protocol is that once a lower priority task is executing its critical section, it cannot be preempted. So, the only thing that can be done is to make it execute as fast as possible. the shortest duration over which it can release the critical section, the higher priority task can get to use the resource and the inversion time will be small. But how do we really make a low priority task complete its execution as early as possible? Given that the protocol is simple, the main idea is that whenever a low priority task is executing, make it complete as early as possible. If you remember, a low priority task which was executing in the critical section was getting delayed by intermediate priority tasks, which are started to use the CPU, and the low priority task could not make progress. So, the solution here is to raise the priority of the low priority task, so that the intermediate priority task cannot preempt it. But then by how much to raise the priority of the low priority task executing its critical section? Let us try to answer that question. By how much should the priority of a low priority task once it is executing its critical section be raised? The answer is that make the priority of the low priority task as much as the task that is waiting for the resource, and therefore, intermediate priority task cannot preempt this low priority task anymore. In this basic priority inheritance protocol, when a resource is already under use, a high priority task that needs the resource makes the request, and all the resources all the requests are queued in the FIFO order, and the inheritance clause is applied each time a high priority task requests a resource and is waiting. The low priority task's priority is made equal to the highest priority task that is waiting for the resource. That is the simple protocol. Whenever a higher priority task blocks for the resource, the lower priority task inherits the priority of the highest priority task that is blocking on the resource. So, this is an example here. Low priority task holding the resource, high priority task waiting for the low priority task to complete uses of the resource, and the priority of the low priority task is raised to be equal to the high priority task, so that the intermediate priority task cannot preempt the low priority task, and this is called as the priority inheritance scheme. Let us look at some more details of the scheme, the nitty-gritty of the scheme. Here, once the high priority task blocks for the resource, the low priority task's priority gets raised to the highest priority task in the queue. If there are two tasks which are waiting, one is medium priority, one is high priority for the resource, then the low priority task that is executing using the resource gets the priority of the highest of these two. So, which is H. But then once the low priority task completes its usage of the resource, it gets back to its older priority. The low priority task again becomes low priority, its priority value changes once it releases the resource, unless it is holding other critical resources. Critical section and high priority task is waiting, it inherits the priority of the high priority task that is waiting, and as soon as it releases the resource, it gets back its original priority. But then let us look at the problem it creates and the problem it solves. It solved the problem of unbounded priority inversion. But how does it solve unbounded priority inversion problem? It solved the unbounded priority inversion problem because in the inheritance clause, the priority of the low priority task is raised to the priority of the high task that is waiting, high priority task that is waiting, and therefore, the intermediate priority tasks that were preempting the low priority task from CPU users cannot do so, and therefore, the unbounded priority problem is solved. The intermediate priority tasks can no longer preempt it, and the unbounded priority problem is solved. This is just a representation, schematic representation of the working of the priority inheritance protocol. Let us look at it. A low priority task is holding a critical resource and the priority value is 5, that is at time instant 1. After some time, that is time instant 2, a high priority task started executing and its priority level is 10. After some time, it needed the resource and it blocked because the resource is already being held by the low priority task. It started executing, shown by green, but then its priority changed because a high priority task is waiting. The priority changed from 10 to 5 due to the inheritance clause. Sorry, once it starts waiting, its priority changes from 5 to 10 and it keeps on executing as a high priority task with priority 10, and then as it releases resource, it gets back its own priority value. We are at the end of this lecture. We will continue from this point in the next lecture. Thank you.